Hello, I'm going to talk about Monodic Neighborhoods again in this video, and I'm going to talk about two aspects. One is neighborhood charge, and the other is neighborhood binding depth. And I'll start with the latter first, and then talk about charge last. So I'm going to draw a general neighborhood, the J, and then these indicate that there's a charge and then a binding depth here, and that'll make more sense as I go along with an example. So the first example will be for binding depth. Let me make that a little bit bigger. So I want to essentially nest a neighborhood within a neighborhood. I'm just going to write that up there so we have it. So binding depth, and I can't really read that very well, but anyways. So, and then I'll just label these. It doesn't matter what. And like I said, we're just kind of using a generic neighborhood, right? And so this whole idea is like definitely inspired by Gheorghe Păun, Gheorghe Păun, I believe that's how you say it, who developed P systems, which were a abstract system of representing biology using like mathematical concepts. And so he developed this idea of trying to understand nesting in that sense. So kind of very, very similar to what they call membrane computing, just kind of like where the P systems kind of evolved to and where they work in that theory. So with this, we're talking about neighborhoods nested within neighborhoods. So this neighborhood's nested within this one. So now, when there's no nesting of a neighborhood, then the binding depth is 0. And there's no such thing as negative binding depth. It doesn't. It's not built in implicitly in monodic theory. It's obviously could be something later on, but it has to be defined as such. And then since this is within one neighborhood, so the binding depth of 1. So you kind of get a sense that there's something inside and something else, right? So you got one neighborhood inside another, and they're distinct neighborhoods. That's really the main idea behind it. You could show in a graph sense, make it look like it'd be very similar to like a tree. Like if you took, let me erase this real quick. You took and for each neighborhood, say that's 0, 1, so on and so forth. You can make it like tree-like, right? You could say that this has a mono here, blah blah. You know, you could say this is a self-binding one, or you can say this is another mono. Anyways, that's not right. Oopsie. Okay, something like that, right? So you can kind of get an idea, sense that there could be like a tree-like element to this if you're using that tau equivalency. But that's really the idea behind binding depth. Pretty simple. Definitely we'll go into some more elaboration on that later on in later videos. So now I'm just going to get rid of that B and say, okay, so we got this charge right here. So this C can be replaced with a plus, a minus, or a mu. And what this means is everything inside, and I'll just use illustrate this. Everything inside this neighborhood, say it has that. So if it has the two negative charges, then the charge is going to be negative. So if all the monodes inside the neighborhood are a certain charge, then the entire neighborhood has that charge. And it kind of goes the same way. If this is a plus, right? Now, but what if we have something where it's a plus minus? Well, not all the monodes inside that neighborhood have the same charge, so it wouldn't make sense to put a minus or a plus right there. So my idea was using the moo, because the moo gets is a good replacement for when things don't really make a lot of sense. Like there's not really a simple answer to there. It's very catch-all kind of symbol. It has a lot of like functionality behind it. Well, this is just one of those. And so if you have two monos that don't have the same charge, that's all that's inside that neighborhood, then you get the moo. And there's really not much more to it than that. You could do probably some interesting things later on with trying to understand how to look at the differences between a neighborhood that has a full positive charge and one that has a moo charge, uh, essentially mixed charge, and then kind of compare and contrast. You could do some stuff like that. But that's really it for these two. And then I think later on I'll go into more depth and just kind of try to work out any problems or issues that might show themselves. But if you're watching this, thank you. Appreciate your spending your time watching these, what I find interesting videos on monadic theory. So, and don't be afraid to make comments and stuff. I'm willing to listen and address them if need be. If I am need corrected, positive criticism, anything like that, I'm all open for it. All right. Well, thank you.